All right, let's dive into one of the coolest puzzles in all of chemistry. We're talking about a phenomenon that basically gives molecules a secret identity. It's all about how you can have the exact same ingredients but end up with something completely different. Let's get into it.
So let me ask you this. Just think about it for a second. Imagine you're baking 2 cakes. Use the exact same recipe, same amount of flour, sugar, eggs, everything. But one comes out perfect, and the other is just a dense hockey puck. Well, believe it or not, this kind of thing happens with molecules all the time. But how is that possible?
And hey, this isn't just some theory. Take a look at this. We've got 2 compounds here, butane and 2-methylpropane. Now look at their chemical formula. It's exactly the same, C4H10. 4 carbons, 10 hydrogens. But then look at their boiling points. Butane boils at -0.5 degrees Celsius, while 2-methylpropane waits all the way until almost -12 degrees. That is a huge difference. Same parts, totally different behavior. This is our mystery. And lucky for us, this mystery has a name. It's called isomerism. And this is the absolute key to what we're talking about today. It's this idea that you can have molecular twins. They share the exact same formula, but the way their atoms are actually put together, their 3D architecture, is different. And that different arrangement changes absolutely everything.
So, how exactly do we shuffle these atoms around? Well, let's start with the most direct way, by changing the molecule's fundamental blueprint. These are called structural isomers.
With structural isomers, it's pretty straightforward. We're literally changing which atom is connected to which. Think about it like having a set of Lego bricks. You can connect them in a different order to build a totally different shape, right? That's exactly what's happening here.
Okay, so let's start with the simplest type. We call it chain isomerism. Look at butane on the left. It's just a nice straight chain of 4 carbons. Simple. But using those exact same 4 carbons and 10 hydrogens, we can build the molecule on the right, 2-methylpropane. All we did was pluck a carbon off the end and stick it in the middle. Boom, we've created a branched shape. Same parts, totally different carbon skeleton.
Next up, we have position isomerism. Now in this case, the main carbon chain, the backbone, actually stays the same. See these 2 molecules? Both have a 3-carbon chain. But notice that little OH group, the part that makes it an alcohol? In propan-1-ol, it's hanging off an N carbon. But in propan-2-ol, it's just moved over 1 spot to the middle carbon. The backbone's the same, but a key feature has changed its address. And now for the most dramatic one of all, functional group isomerism. This isn't just moving a piece around. This is a total rewiring of the molecule. On the left, we have something called propanoic acid. It's a carboxylic acid. But on the right, using the exact same atoms, just rearranged, we've made methyl ethanoate, which is a completely different type of molecule called an ester. They're in totally different chemical families. It's like taking all the parts for a car and somehow rebuilding them into a motorcycle. And if you want to see just how big a deal this is, look at this. Here we have 2 more functional group isomers. The acid boils at a whopping 164 degrees Celsius, while the ester boils at just 77. The acid dissolves really well in water, the ester not so much. This is the whole point. Just by rearranging the same atoms, we've created 2 completely different substances with wildly different properties.
Okay, so we've seen what happens when we change the atom-to-atom connections on the blueprint. But what if the blueprint is exactly the same? What if the list of who's connected to who is identical? Is it still possible for them to be different molecules?
The answer is a huge yes. And this is where things get really cool. Because to understand this, we have to stop thinking in 2D drawings on a page. We have to start thinking in 3D. Welcome to the world of stereoisomers.
Stereoisomers are just fascinating. They have the exact same structural formula. That means every atom is connected to the exact same neighbors. The only difference, the only one, is how they're arranged in 3-dimensional space. The instruction manual is identical, but the final building just has a different shape.
A perfect example of this is geometrical isomerism. You see that carbon-carbon double bond right in the middle? I want you to think of that like a hinge that's been welded shut. It cannot rotate. It's locked in place. And because it's locked, the other groups are stuck. In the cis isomer, you can see the 2 CH3 groups are stuck on the same side, but in the trans isomer, they're stuck on opposite sides. Same connections, but 2 totally distinct 3D shapes that can't change into one another.
But there's an even more subtle, even more mind-bending type of stereoisomer out there. And to understand it, we need to think about something we're all very familiar with: mirror images.
Okay, do me a favor. Hold up your hands. They're perfect mirror images of each other, right? Now, try to lay your right hand perfectly on top of your left hand so they match up, palm to palm, thumb to thumb. You can't do it. They don't line up. They are non-superimposable. Well, some molecules are exactly like this. They have a left-handed version and a right-handed version.
And these molecular twins, these non-superimposable mirror images, they have a special name. We call them enantiomers. They are identical in almost every way you can measure. Same boiling point, same melting point, same density. But at the end of the day, they are fundamentally different 3D shapes. So what's the secret ingredient? How does a molecule get this handedness? It all comes down to something called a chiral carbon. All that means is that you have a carbon atom in the middle that's bonded to 4 totally different things. That asymmetry is the magic trick that makes having a non-superimposable mirror image possible.
This leads to a really interesting problem, doesn't it? If these enantiomers have identical physical properties, like their boiling points, how in the world can we tell them apart? How do you know if you're holding a flask of the left-handed stuff or the right-handed stuff?
The answer is just so cool. It's light, but not just any light, a special kind called polarized light. When you pass this light through a sample of one enantiomer, it will actually twist or rotate the light in one direction, let's say clockwise. Then, if you take its perfect mirror image twin, it will rotate the light by the exact same amount but in the opposite direction, counterclockwise. This amazing property is called optical activity, and it's our secret weapon for telling them apart.
So let's bring all this together. What's the grand takeaway from all of this? From simple chain swaps to these tricky 3D mirror images, we've seen that a molecule's true identity is so much more than just a list of its parts.
It really all comes down to this. Isomers have the same formula but different structures. If the connections themselves are different, they're structural isomers. If the connections are the same, but the 3D shape is different, they're stereoisomers, which includes those cis-trans ones and the mirror image enantiomers. And at the end of the day, it's that 3D architecture, that shape, that decides what a molecule can and can't do. So if you remember one thing from all of this, let it be this. In chemistry, it's not just what you're made of, it's how you're built. Shape is everything.
And that leaves us with one last really big thought. In biology and medicine, the shape of a molecule is what makes it a life-saving drug or something completely useless. So I'll leave you with this question to chew on. If a molecule's shape defines its function, what happens when we finally learn how to build any shape we want?